Good day, all. We're trying to prove something about perfect numbers, so I'm going to talk just briefly about what we mean by a perfect number. Like if you have, let's say, sigma of 6, okay, this is the sum of the divisors of 6, okay? And we're trying to show that a square integer is not a perfect number. Now notice, again, this sigma function sums up all the divisors, including 6, so this would be 1 plus 2 plus 3 plus 6, okay, but that's equal to 12. But notice that's equal to 2 times 6. So this motivates a definition for what we mean by a perfect number. I'll use m, I guess. Sigma of m is a perfect number provided that sigma m is equal to 2m. Okay, like that, all right? The next one I think is 28, and after that is 496, and you guys can check that. But we're just here, the purpose of this is to define what we mean by a perfect number, okay? Now we're going to try to show that a square integer is not a perfect number. And so arbitrary integer always has a canonical prime factorization. These alpha sub i's could be 0 also, I think, but we're going to just take them to be positive integers. And also, of course, the p sub i's are prime, okay? All right. Now, since we're talking about the square of an arbitrary integer, we're going to square that arbitrary integer's prime factorization. And this certainly results because if you have, like, let's say a to the m, let's say, raised to the second power, just basic properties of exponents indicates this is a raised to the 2m, right? Okay, so that's what happened. This step to this step, okay? Let's keep moving. Now, this is a result that actually sums up the number of divisors of n squared based on the prime factorizations. This is based on a finite geometric series, basically, and I'll just leave it at that. I'm not going to attempt to prove this. The proof isn't as hard as you might think. Just remember, it's a product of a bunch of finite geometric series, a bunch of primes, individual primes summed up, powers, okay? Now, so we're going to do the standard proof here. That's a lot of people contest the validity of a proof like this, but we're going to go ahead and assume that n squared is a perfect number. And so we're just using this definition here, right? Sigma of m is equal to 2m means m is perfect. Okay, that's exactly what I've done right here. I'm assuming that it's equal to 2n squared, where n squared is our input argument, so we get this. Now, if we carry on, we get this, we just divide through by the prime factorization of n squared, and we get this statement. And the very next thing, what we do next is fairly natural, folks. We just use properties of exponents. You see 2 alpha 1 right here. Okay, if you put it right underneath this one, all that's left is p sub 1, right? Okay, all the way across, you put this one directly underneath this. You get p sub 2, and of course you have 1 over also, okay? So that happens all the way through. Okay, now what do you do about this? Okay, it still looks kind of messy, right? But one cool thing that we can observe right now, and I'll just circle this one, but all of the numerators have this property. Okay, this is the numerator that we got by dividing this into this, right? Okay, but notice this is a member of what a lot of people, I've seen backslash used too, but we can call it Q, where Q is the rational numbers, minus. This is set theoretical. Right here, folks, what this is saying, set theoretically, this is the set of rational numbers, this is the set of integers. So this object right here is a member of this set. Another way of saying that in relatively plain English is that this is a fraction that is not an integer. For example, 7 over 1 is a fraction, right? It's a rational number, but we're not interested in that here, okay? It's also an integer. So we're subtracting off the set of all the integers from the set of rational numbers. Now you see that's cool, because that means this whole thing, if you take a rational number that is not an integer and divide it by an integer, you still get a rational number that's not an integer, and the same all the way across, right? So you see what we have here is an impossibility. This is impossible, as Underwood Dudley would say. This is an impossibility. And we reach this, and again, y'all, I may be overkilling here, but we have a bunch of real rational numbers, genuine, authentic rational numbers, and they're going to be closed under multiplication, so that can't result in an integer, which you have right here. You have an integer 2. This product cannot possibly be the product of a bunch of real rational numbers, okay? Okay, not fake rational numbers, right? So what did we contradict? Well, we contradicted this statement right here. We supposed that n squared was a perfect number, and we got a contradiction. We supposed it was a perfect number. We got a contradiction. We spoke against ourselves. Contradiction. Okay. Okay. So that finishes the proof, folks. QED. Thus we've demonstrated. Okay, everybody, that's it. Thank you for reviewing. I kind of like this. I haven't quite seen this exact proof. This is a standard proof in a number theory textbook. I haven't quite seen it done this way. Probably it has been. I just haven't found it. But anyway, thanks for reviewing.